Assalamu alaikum. So today we'll be studying about the reaction of phenols basically. So we'll be continuing with where we left over. So without further ado, let's begin. So reactions of phenol. Now, what are phenols actually? Before writing reactions of phenol, let's consider what are phenols. So phenol, let's go to another page. So working with phenol at first, what are phenols? So phenols are benzene-like structure with a OH group. Now you might be thinking, okay, now this is an alcohol. No, this is not an alcohol. Basically, this is OH group, which is a hydroxy group, reacted or formed bond with the benzene molecule. So that's basically it. And when it is dissolved into water, it sort of undergoes a partial ionization reaction, forming O minus and H plus ions. That means phenol is acidic. So this is acidic. Since it can produce H plus ion in like aqueous solution, so it is acidic. Now, moving further into that, before that, we sort of will try to observe actually what type of reaction phenol participates. So the first reaction, like, why am I saying before giving any explanation or phenol is like, because it will make things easier like in today's class. So phenol is acidic. So since it is acidic, that means the reaction with a carboxylic acid will be what can be the product formed. With the general knowledge, can you try to like make sense? It might be that we would try in such a way that we would think this is an alcohol, so OH group, and this is a carboxylic acid, and we know from our AS contents that carboxylic acid plus alcohol forms ester. So there must be this ester linkage, which is C double bond O, and the molecule like continues. So this could be, let's say, so for a certain moment, we would be thinking that this can be the product which is being formed. This is the acid part and this is the alcohol part. But the reason I also wrote acidic here is phenol is acidic. And this is actually not the way that like alcohol works. So this is not actually alcohol. This is, as I have mentioned in the like at the beginning of the class, that phenol shows or dissociates an hydrogen ion. So that means if one of the other compound forms hydrogen ion and this also forms a hydrogen ion, they are going to repel each other, isn't it? So both are positively charged and both are having same sort of characteristics. That means this reaction is not going to happen. So no reaction. Okay. Now the second reaction I want to talk about is, let's say this is the phenol again. Now I have provided NaOH, sodium hydroxide, instead of carboxylic acid now. Now try to guess what could have been formed. Same concept, this is acidic, that means it doesn't react as alcohol. What is this? This is the base, alkali. Acid and alkali, they react together to form a neutralization reaction, participate in a neutralization reaction. That means the reaction should have been OH, sorry, not OH, it should be Na, so Na plus and O minus actually. So this is an ionic equation, like ionic reaction happens there. And the other product is water, because neutralization reaction is happening. So this is what is being formed. And this, like for the like convenience, I can also say you the name of this molecule, which is sodium. So sorry, not N, it's SODIUM, sodium phenoxide. Sodium phenoxide. Phenoxide in terms of like phenol. So that means we got to know that this ion formed by phenol is phenoxide. an oxide. The last reaction I want to talk about is, let's say we have this phenol molecule, and with it I'm adding sodium. Now, what usually happens if we, like, obviously this won't be like easy for you to understand, like if you like easy for you to guess, but what happens here is, this is an acidic solution, and we know acid plus metal tends to form a salt, and then like they tend to react. So here as well, this sodium is going to react with this OH. So this sodium is going to react with OH, forming the same Na plus and O minus. So this is the sodium phenoxide, and with it the hydrogen. So that means half of hydrogen. Yeah. So now it is balanced. So this is like, these are the three reactions, or sort of main reactions, which phenol works with. So we will be talking about this sort of reaction today. So my main idea for like initially giving the concepts of how this reaction occurs is like, why phenol participate in this sort of reaction. One thing to notice here is, over here, it is actually a redox reaction. This reaction is actually a redox reaction. The previous reaction was what? A neutralization reaction. This was a neutralization reaction. Neutralization reaction. That means our phenol, it is actually participating in several reactions, like different types of reaction. Obviously, the first one does not participate in reactions, no, like any reaction. So this is a no reaction, no reaction reaction. So neutralization reaction, it is like understandable, but why redox over here? Like, what's the big deal? What has happened? Try to observe this. Sodium here has a charge of what? If we observe the charge of sodium, it is what? 0, neutral here. But over here, what is the charge of sodium now? +1. So the oxidation number increased. So that is, it has been oxidized. Now think about the hydrogen. Hydrogen here is having a charge of +1. But over here it is neutralized. It is having a charge of 0. That means the oxidation number decreased. So reduction. I mean, the oxidation number decrease means it is reduced. Like it is sort of gaining an electron, because sodium is losing electron to form positive charge. So hydrogen is gaining that electron to form, like, so that plus and minus, the negative charge from electron and the positive charge from hydrogen, they cancel out, and hydrogen becomes neutral. So what is happening? Reduction is gain of electron, or reduction is decrease in oxidation number, and oxidation is increase in oxidation number or loss of electron. That is, both reduction and oxidation is occurring in the same reaction. So this reaction is a redox reaction. Okay, so now let's come to the phenol's property. Since this was an acidic solution, so in phenol, there is actually a lone pair of oxygen, or lone pair of electron in the oxygen. Like in this oxygen, there is a lone pair of electron. Lone pair of electron. Now, what does this lone pair of electron means? This means that there is a pair of electron in the oxygen molecule over there, which didn't form any bond. That was like completely isolated. Maybe the other electrons, let's say one of the how do I say? Let's say one of the electron from oxygen bonded with our carbon atom. So there's just that bond, and one of the oxygen bonded with a hydrogen atom. So there's that bond. Okay. Now 1, 2, 3, 4, 5, 6, and there were somewhere, let's say, some other lone pair of electron over here. Okay. Now, I'm sorry, like there are like 2 lone pair of electrons. So actually there are lone pair of electrons. So this, like, maybe let's consider one of the lone pair of electron is actually doing some sort of like unusual work. So what is happening? That one, that lone pair of electron, it is actually delocalized with the pi electron. So that means that like this lone pair of electron, where like there are like extensible amount of like extra electrons. Okay, with this bond, like this is the portion for the benzene part, isn't it? Now below here we have the benzene ring. Now, if there are, let's say, like extra electron pair, that electron pair tends to delocalize or like gets pulled by the benzene ring. So if there are like this electron pair, now this electron pair, they sort of cannot stay here for much longer. Why? Because they are going to get pulled by this pi ring. So the pi ring will be pulling them towards them, and let's say it will be like revolving around this. Like it will be delocalized. Delocalized means it will no longer stay where it stays usually. So the electron pair will no longer stay there. It will come below. Now, if let's say the electrons are pulled away from oxygen, then what will happen? There will be less number of electrons here, so the negative charge will be like weaker here, isn't it? Because negative charge is based on what? Stronger electrons. I mean, the greater the number of electrons present, the stronger is the negative charge. So electrons being pulled away from oxygen, that means oxygen has a less, like weaker negative charge. So that means this hydrogen, obviously hydrogen's electrons are not pulled. Hydrogen has its electron with it itself. So hydrogen's positive charge remains unchanged. Okay, it is like as strong as it was before. Since oxygen has a weaker negative charge, it is unable to now attract this H plus ion. It is unable to attract that H plus ion as it was before. Since that's the case, this hydrogen ion is more willing to stay free, roam around in the solution, than staying in the bond, like staying and forming the bond. That's why H plus is more available in the solution. As a result, since like H plus is more available to the solution is acidic. Now, as this oxygen actually cannot pull anymore, like this oxygen cannot pull the hydrogen ion, H plus ion, as strongly it was supposed to be. The bond actually, this OH bond over here, it tends to it forms a weak bond now, isn't it? It is now acting as a weak bond. So OH bond becomes weaker because it makes sense that if oxygen is unable to pull that hydrogen towards itself, the bond is going to get weaker. So the bond is now weaker. Now hydrogen ion, as I've mentioned, it is formed, and phenol ion, the phenoxide ion, is stabilized. Now, what does this stabilized mean? Stabilized mean in whichever state I am. Let's say I am currently, let's say, an intermediary carrier person. Now, or let's say someone living in USA is an intermediary, just started his job. At the mid age, let's say at the age of 30 or 40, he earned around, let's say, $10 million. Okay. Now he tend to think, okay, all the expenses and everything is going to get weird. So it is going to cover up all the expenses up until my retirement, and even after retirement. Okay, then that means I'm now stabilized. I can now chill around. So I can relax and do all sort of funny things. I can now no longer I need to be on the game. So that means it is stabilized. So that's what also means here, this is no longer is reactive. Now stabilization, the other term can be mentioned here is the stabilization could be a synonymous term for not reactive. Now reactive means unstable. Reactive means which are unstable. That means they are willing to react and form a stable electronic configuration, as like the noble gas. Noble gases are all stable, but that means those are the substances which are reactive, they're unstable, they want to become stable. But in this case, since the electrons are taken to the benzene ring or the pi ring, this phenoxide ion is it has become now stable, because the negative charge on it's very weaker, so it is unable to form any more bond. So it tends to be by itself. It is now less reactive, so it is now more stabilized. Hence, the charge is actually happening what? The charge as well is delocalized. Okay, so that's basically the reason for phenol being acidic. Now, let's have some comparisons. Ethanol is which one? Ethanol is CH3, CH2, OH. Okay, that's the alcohol I'm talking about. So if we draw the discrete structure, this is the alcohol. Now this ethanol, when I dissolve it into water, let's say I want to like I also am like I'm imagining, or I want to make it react in this way, like delocalization. Obviously, phenol does not actually causes this had to happen, but I'm imagining. Let's imagine that the phenol is actually sorry, not phenol, ethanol. Ethanol is actually like partially ionizing itself, okay, forming H+ ion in the solution. But according to the record, or according to the study, ethanol is neutral. Now, why is it? Like, why is this? Like, why is that the case? Let's think of this part. In like while we were studying the terms acid dissociation constant and the like those constant terms, you'd see if you revise those chapters that we have learned that these alkyl groups, they are electron releasing group. That means they are electron donating group. So the electrons from them, they tend to push towards the electronegative molecule. Now, which one of this molecule or which one of these atoms are electronegative? Oxygen is the electronegative. Okay, this is the electronegative atom. So this ethyl is electron donating, so it donates or pushes electron away from itself. This alkyl also pushes away the electrons, moving electron towards oxygen. Now, like the oxygen atom has what? Greater number of electrons. Like the electrons from them are now deposited to oxygen. That means oxygen in this case have like greater number of electrons. That means the more the electron, the stronger is the like charge or negative charge. So this stronger negative charge is able to do what? When H+ is formed in the like ion, this is actually willing to attract strongly this H+ ion. Why? Because this is now reactive, very reactive. They want to like neutralize. They want to become stable, or this like ion want to become stable. But it is currently unstable. Due to its instability, it attracts this H+ ion, forms bond with this H+ ion, going to the reverse direction and staying more in this situation. That means in this situation, it is much more stable. Okay, in this situation, it is much more stable than here. This here, it is unstable. But what happened in the like previously phenol's part? In like phenol's part, this was like unstable. Okay, this was unstable. But over here, this phenoxide, it becomes stable. Why? Because our H+, sorry, our O minus was very weak. Unstable in this case because this OH bond is weaker. Okay, this OH bond is weaker and the electron has been taken. Now, oxygen is now willing to actually lose like hydrogen or lose the positive charge. It is like willing to, okay, like you can go. I'm not like willing to keep you now. So that's why H+ is like moving away from the oxygen atom, and hence this like a stable configuration is formed here. On the other hand, for ethanol, it is the opposite. Now, as I mentioned, this ethyl, like the ethyl group or the alkyl groups here present, they are what? Electron releasing group. Due to that electron releasing group, electron is pushed towards this oxygen, like the oxygen atom. Now, when like we consider this ionized situation, this is known as the ethoxide ion. Ethoxide, OXID, ethoxide ion. Now, this ethoxide ion tends to be what? Tends to be very unstable. Now, due to this unstable like characteristic, due to the like presence of this alkyl groups here, ethyl group, which are the electron donating group, it tends to attract or pull H+ ion towards itself and like combines with it. This O minus tends to combine with this OH plus in this ethoxide ion. Hence, no hydrogen ions are actually like produced here because this ethanol is stable by itself. Okay, that's why ethanol is neutral. Now, if I talk about another comparison, let's say water. What happens with water? Water, it is, we know, as like we have studied earlier, that it is partially ionizable. It sort of like it actually ionizes itself in the water, like in itself, it breaks down. So water is actually like undergoes this reaction because water, like we know, like they tend to form this partial, like very partial ionization reaction. Though this is actually delta plus and delta minus, but we can write actually plus and minus here. But this acidity of water, okay, so water is actually a little bit acidic. Water is not actually completely neutral, it is a little bit acidic. Though this acidity won't like harm us, like as we drink water, but this acidity is much like, this is more like, water is more acidic than ethanol. However, phenol is much more acidic than water. So if we tend to compare or write there like acidity, let's say diagram, so towards the, from left to right, acidity increases. So that would be something like this. Initially it is C2H5OH, which is our ethanol. This is ETH, let's say ethanol. And then we have water, which is this. And finally we have C6H6, oh no, is it C6H5OH? Yeah. So we have our phenol. This is much like, this is the strongest in acidity. This is the like a bit weaker, and this is the weakest. Now let's continue with our like, progress. Some information to be given is phenol is more acidic than benzene. Phenol is more, sorry, more not acidic, it's more reactive actually. It's more reactive than benzene. Okay, so now how its reactivity could be like identified, or how can we work with or analyze its reactivity? So let's say we have a phenol molecule here. Pardon for my drawing. Now, in a state of room temperature, RTP means room temperature. Let's say we added nitric acid, okay, HNO3, which is nitric acid. Now, when this reaction is happening, what is basically happening? Phenol reacts with this our nitric acid in terms of electrophilic substitution. As I've mentioned, the characteristic reaction of benzene is what? Electrophilic substitution. Now you might be saying, you just mentioned this is phenol, and you are saying phenol is more reactive than benzene. Obviously, there are then two different molecules. Sorry for that. Yes, obviously they're like different, but they have same characteristic as they have the benzene ring. Obviously, let's say if I have two hands, okay, or let's say someone has let's say one hand. Now the person who has a single hand and the person who has two hands, obviously their capacity or capability to do certain work will differ, isn't it? Someone will be able to will be more efficient while the other will be less efficient. So, or the robot, let's say, in terms of like, that wasn't a good example. So Mela like help all those who are having difficulties. But let's say in terms of robot, I made a robot, let's say, who has, let's say, a single hand, and the robot who has like two different hands. Okay, so the robot who has two hands will be able to, let's say, pick up greater stuffs compared to the one who has single hand. So that means their capability or ability to do certain work differs. Similarly, a single, let's say, just a single difference in the molecule, that also makes a like great difference in like in case of their like reactivity. Just bear with me, you will get the gist right now. So this is the nitration. This reaction is actually known as the nitration reaction of phenol. So nitration of phenol. This is actually the like all those who will be having this benzene ring, the pi ring inside, they will be participating. Like if we are like working with this part, okay, only this part. If we are not having any side chain reaction, if we are not having any side chain reaction, that means the parts which will be over here on the like the outside of this benzene part, those will be different. Those will be having different sort of reaction. But the reactions which will be having with this main part, the benzene part, the benzene structure, that will be happening, or that will be undergoing the reaction which is electrophilic substitution reaction, because that's the electrophilic substitution, because that is the characteristic reaction of benzene substitution. Now, so now actually what is happening, what will be happening is the alcohol, I mean, sorry, the phenol is, the phenol will remain as it is, but this nitrogen, since nitration reaction is happening, there will be this nitroxide group or NO2 group, which will be either in the second carbon or in the fourth carbon. So remember, as we have studied in terms of our Friedel-Crafts alkylation, so it based on that thing, either for like, if it's like, since the first carbon is like bond, like having a sort of bond with some substance, the next possible electrophilic substitution will take place with either second carbon or the fourth carbon. Now you might be saying, what about the sixth carbon? Yeah, like this, like having this nitrogen over here or over here are the same thing, isn't it? Initially, this is the same thing. Like initially, if let's say we didn't have this nitrogen NO2 here, so writing in this way or the other way is same, because like let's say you are observing the monitor or the display from this side. Now let's say somehow you are able to display the, like you were able to like view the display from the opposite side. What would you see? Like what would you see? You would see that the nitrogen is actually on your right hand side. Like since now it is on your left hand side, if you tend to see on from the other side of your display or your screen, let's say if you're using the iPad or some more monitor device, if you somewhere able to, like the display was somewhat like, let's say the transparent, and from the other side you would see what the NO2 actually is on the right hand side. So that's why like both are actually like initially they're same. Now this is actually happening at room temperature, but for the nitration of benzene, okay, nitration of benzene, same benzene ring without the phenol, with same reagent, which is nitric acid. This time we need concentrated sulfuric acid at 55 degrees centigrade. See, the temperature has now like increased. Since like the first carbon didn't have any like bond formation, like any bond with other, like obviously there's an imaginary hydrogen there, obviously there's hydrogen, but except for that there is no other substance bonded with this benzene part, so we can actually form this bond over here. Now thing to be noticed, the point to be noted here is that the title was given phenol is more reactive than benzene. That's why the phenol didn't require any such conditions, like simply giving the reagent at room temperature it reacted. But benzene, giving this reagent at room temperature won't react. We have to increase the temperature so that it excites, it becomes excited, and it becomes like, for example, when it is more hot outside, okay, we tend to like we tend to become more curious or more exhausted, isn't it? On the other hand, let's say if the weather is cold and let's say like winter comes, what happens? We tend to like stay relaxed, stable, like I don't want to work now. But like in summertime, like the more we say, like for example, those who work out or like usually those who dances, what happens? Once you started dancing, like once you started like feel the heat, start to sweat, like you start to do more work, because like once you get the flow, it works in that way. So that means the temperature needed to be increased, because at room temperature it sort of is less reactive. But at room temperature, phenol is so reactive that it reacts without any further conditions. Okay, now how this benzene actually participated in this like phenol reaction, like nitration reaction. Sorry, not phenol, the nitration reaction. So the mechanism, let's say, the mechanism for, let's say, for nitrobenzene, like the formation of nitrobenzene would be what? Initially, it's the same thing, electrophilic substitution. So we need to form the electrophile. Now in benzene's case, we had what? this sulfuric as our catalyst. So this is going to react with this H2SO4, forming HSO4 minus plus H3O plus NO2 plus. This is like one of the single step which you need to remember. There's nothing to be done here. So you need to remember here. Now, which one of them are actually electrophile? Actually, this is the electrophile because we need this one to be reacted or to be formed, like forming bond with the benzene molecule. Now, if we try to balance them, this will be the reaction. This is actually nitronium ion. Okay. Now, in the second step, this was the first step. In the second step, the simple thing will happen, which we have seen so far in the benzene part, in the Friedel-Crafts alkylation, the initial reactions which were shown in the first lecture. So this pyrene will attack this nitrogen or this electrophile, forming, I'm sorry for drawing again, forming this NO2 and this hydrogen. Okay, now this will be partially, like the ring will be partially there. Now in the second, like the next step, the hydrogen will be like the bond or the pyrene will be overcome by breaking the hydrogen bond. So hydrogen carbon bond will be broken, forming NO2 here. So like leaving NO2 behind, forming the bond with H plus N left over. Now in the last reaction, last step will be like regenerating our catalyst, which is H plus plus HSO4 minus will be H2SO4. Now you might be thinking, why here a single mole of H2SO4 is formed? It's completely fine. Like one of the molecule reacted. Okay, so there might be obviously millions of such such particles over there, isn't it? Like in a tiny droplet, there is more than millions of like particles, isn't it there? So just writing one of the reaction is completely fine here, because our ultimate goal is to convert this HSO4 minus to our H2SO4 initial component. Okay. Now coming to our next portion. Now, during the nitration of phenol, what is happening? So while let's say nitration of phenol, when let's say like over here, okay, we added HNO3. Now adding concentrated nitric acid, or like we added here nitric acid, okay, isn't it? So instead of that nitric acid, let's say we added concentrated nitric acid. Now what is going to happen then? Or just wait a minute. Let's say initially we have nitric acid. The reaction we're supposed to be OH and NO2, isn't it? Instead of that, we added concentrated nitric acid and a little bit of, let's say, heat was applied. A little bit of heat was applied. Now, what would have happened? Simply, this portions will be reacted. So that means complete or excess reaction happens. Like every part of the, like every possible places of the phenols, which is possible to form a nitration reaction, will be reacting with this nitronium ion. Hence, a compound which is named 2,4,6 tri-nitrophenol will be formed. Now, why 2,4,6? See, this is the second carbon, fourth carbon, and the sixth carbon. So based on the carbon number, this is actually formed. So nitrophenol. Now, this is our like the phenols part, like what happens if excess of the conditions are being applied. Now, how do we identify phenol? Because at like initially or in our general view, normal view, phenol is like colorless. Because for example, phenols are usually used in cleansing the washrooms. So identification of phenol. Now, there are certain tests. So one of the tests is to add bromine solution. So you might be thinking, this is the same solution which was added for the identification of our alkene. So yes, obviously in alkene there is a C double bond. So that C double bond breaks and decolors the bromine water. Like sort of same concepts happen, like same same test is being added or same reagent is being added, but the observation is different. Observation is going to be white precipitate will be formed. White PPT is formed, and now this white PPT is actually basically due to the like 2,4,6 tri bromophenol. That means when we are adding with this phenol bromine, what is going to happen? Simply OH, Br will be formed. Now remember, for each Br molecule that is able to react with just one carbon, like it is going to form just a single bond, isn't it? For each bromine molecule. Now, the reason for providing 3 bromine is we know bromine is diatomic, but what happened to the other atom? Because one of the atoms just bonded with this carbon atom. The other atom bonded with what? H, hydrogen. So HBr is being formed. So that means from 3 positions, 3 hydrogen will be gone out, and for this 3 bromine molecule, 3 bromine atom will be going out. So that means in total, 3 hydrogen bromide will be formed. Okay. Now, this was actually basically our knowledge based on like the phenol. That was the topic for phenol. The next topic we will be studying, or in our next class, is phenylamine. So I'll be just starting that a bit so that we have a little bit of gist like what we'll be getting through. So phenylamine, which is also known as aniline, ANILINE, aniline. So you'll get questions also named as aniline. So let's say they will, instead of mentioning phenylamine, they will say aniline is being reacted with something. So now this aniline is having a structure of this. This is actually amine group, which is on the on top of our benzene. But why not benzene is mentioned? Why phenylamine? Because this amine is actually, the formation of this phenylamine is like from the nitrobenzene. Let's get back to like how it is actually formed. This was benzene. Initially, when we added HNO3, like nitration of benzene happens, concentrated H2SO4 at 55 degrees centigrade. So do remember the conditions for each of the cases, because they tend to give you like ask you questions to fill up the condition. When nitration of benzene happens, in the second step, if we further added, let's say SN, which is tin, so you can find this tin, like detail about this tin and in the periodic table. So tin is a catalyst here with concentrated HCl, okay, and a little bit of heat, or heat is applied. What happens? This nitro group, it transfers into this amine group, okay. So that is how this phenylamine is actually being formed. They won't ask you why phenylamine named is after, like they won't ask you like why phenylamine named phenylamine, why not benzenamide or something. It's just the name given, which the chemists or the scientists thought was correct to be given. Okay, now how do we identify phenylamine? Identification is the same as phenolification. Is the same as phenol. Our test initially is add bromine solution, okay, and observation is ERB. Observation will be white PPT again, same as phenol, white PPT. Now, why this white PPT was formed? This was basically the same thing. Let's say this was our phenol NH2 plus 3 Br2. Okay, this will form tri NH2. This is Br